Okay, just want to talk today about probability and specifically z-scores and normal distribution. So just a quick kind of background information. So any data that is normally distributed follows the same form when you graph it. So it looks like this with the majority of the data in the middle, hence the peak. So basically this is kind of like a frequency graph. So the more people are based around the middle, and there's very few people based at the edges. Okay, so this graph represents data that is normally distributed. It's also known as the bell curve for obvious reasons. It looks like a church ship's bell, and here's just an example below because people might not necessarily see those anymore. And the idea basically is that this line, red line going down the middle, basically is exactly halfway. Half the data is below that, half the data is above it, and that is the mean. Okay, to the 1, 2, 3, the -1, -2, -3, that is basically if you move out to the number 1, that is 1 standard deviation away from the mean. 2 means that's 2 standard deviations away from the mean. 3 is 3 standard, and so on. Okay, so it's symmetrical. You can see it there either side. The benefit of having data that is normally distributed is that the data is spread out similarly, regardless of whether you're talking about test results, heights of Irish people, number of children in a family, wage levels, number of cars, herd sizes, whatever. In every normal graph, the very center is where the mean is. So every other piece of data is described in the context of how far away from the mean that piece of data is. So how far away from the mean is basically your z-score. Okay. More specifically, and this is from a website here, a z-score is a measure of how many standard deviations below or above the population mean a raw score is. So basically a raw score is just any piece of data. So your test results, how far away were you from the class mean. Just a quick recap on standard deviation is a measure of disbursement. Disbursement tells you how much your data is spread out. Okay, so specifically it shows you how much your data is spread out around the mean. For example, are all of your scores close to the average, or are lots of scores way above or way below the average score? So the smaller the standard deviation, the more clustered the data is. So for example, if you pick a school, that would have a very small standard deviation because everybody in that school is going to be, in a 5 or 10 age range. Whereas if you go into a shopping center, for example, you could have a newborn child all the way up to someone who's in their 90s. So the standard deviation you would expect in the general population to be a lot wider than somewhere like a school or maybe a workplace where everyone is maybe in their 20s, 30s, 40s. So the benefit of, why do we need z-scores, you ask? The benefits of working on z-scores is we can compare that from two different contexts. So once something is normally distributed, then the z-score can tell you information. You can say, okay, well, I did better in my maths exam because my z-score was higher than in my English exam. So basically I was higher above the mean in maths than I was in English, for example. If we were asked, so the symbols or the terminology then it's probability. This is a branch of probability, so we use that P symbol. Z obviously for z-score, and then we have less or less than or equal to, and it doesn't matter, you can interchange those because the difference between them is so infinitesimally small that there's no difference basically. So if we're asked to find the probability of someone having a z-score of less than or equal to 1.3, what we're being asked basically is find the probability that the result will be less than or equal to 1.3 standard deviations above the mean. Okay, we look up the value of 1.3 and find that. So basically we look it up in your tables, and we'll go through that now in a minute. It ended up being 0.9032. So that means that 90.32% of the population will it give you an answer of less than or equal to 1.3 standard deviations above the mean. Okay, and then in graphical terms you can see that's what that means. Okay, so this could be basically, are you in the top, this person here will be in the top 10% of whatever they're specifically specifically marking or testing. Okay, so the graph is symmetrical, so 1.3 standard deviations above the mean is exactly the same distance from the mean as data that is minus 1.3 deviations. And when we go looking at our table, normal distribution table, it doesn't give you negative values, so you have to basically switch them over to the equivalent positive value and work backwards from that. Okay, so we have just a couple of examples here. If you're given the z-score, if you're given the z-score and asked to find probability, follow the examples below. So just have a couple of examples, straightforward examples enough. Where I said about there not being any negative ones, if you just skip down to part 3 here, you can see there you're asked to find the probability of z is greater than or equal to minus 0.56. So what we do is we do a quick sketch of 0.56 and we say, okay, if it's greater than minus 0.56, that's the equivalent of everybody below 0.56, the positive 0.56. And so you just go find that in your tables, and that's the exact same amount of data or amount of people, depending on the context. And you can see the table over here on the right hand side, and we'll go through an example of how to use that table. Okay, it's just a quick thing there. In general, pz less than minus a negative value is equal to pz greater than that value. If you're given the data, mean and standard deviation, you find the z-score using the formula below. So a lot of times you're not given the z-score and you have to go and work that out first before going and finding out your probability. Okay, once you have that, you can find the probability using your maths tables, the formula book that you have, or you have your own normal distribution table to hand. If you have the formula and tables, they're on page 34, or start on page 34. This formula is on page 34 of your tables. If x is normally distributed with a mean of that and standard deviation of that, they're the symbols, then the formula for converting x, which is just any piece of data, to a z-score is given here. Okay, so you're given that formula there. All right, so that's the formula, and these are the steps. So you convert the x value to your z value first. As always, you draw a quick sketch to just give you an idea of the size of the group that you have, and then you go and look up the table to find the required probability. Okay, so if we just a quick example here, we're asked to find the probability, the percentage of the normally distributed population that lies within one standard deviation of the mean. So you can see there we've written it out. Again, because we can't work with negative values from a table, we have to convert them. So you can see the conversions around there. A quick sketch to give you a general idea of what you're looking for, and then you're just going looking in the tables. Okay, and then down below here we just have another example, and we're just going to go through that example, how you actually go looking up that from a tables. So we're asked to find in this case here, we're asked to find the value of k. So we don't know what the z-score is, we just know that the probability is 0.9671. And when you look at a normal distribution table, all the data in the middle, the meat, the main data, that is the probability. The data on the outside are the z-scores. Okay, and you combine those together. So we're looking for 9671. So basically you go into the middle of the table and you look for 0.9671. You see here I have it circled, and then you track across to the left, and this is going to give you your z-score. So you can track across to the left, you see that it's 1.8, and then you track up. Okay, so it has to have the two coordinates 0.04. You add those together and you get 1.84. Okay, so that basically means 1.84 standard deviations above the mean. Okay, so that's telling us that 96.71% of data lies below 1.84 standard deviations above the mean. And it's just, again, a quick sketch there to show that yes, the bulk of the data is below that value. Okay, another kind of a real world problem where you're not given a z-score or probability. Life expectancy of a newborn baby in Japan is normally distributed, so it gives you the mean, it gives you standard deviation, and it gives you the raw data that you're trying to work out. So we have our pieces that we have our ingredients for our formula, our recipe, which is z equals, you have your z formula there. So we'll take our formula, we're dropping in our values, 100 minus 81 over 8, and we get 2.375. Okay, so 2.375, again, a quick little sketch says, okay, that is the bit above that, 2.375. So quite small, you can see it's going to be quite small. So basically, the statement is less than 1% of Japanese newborn babies will live to be 100. Okay, so that is the percentage there, and you just need to work out now the percentage of that. Okay, so we work out, well, what's the probability of Z being greater than that? So that bit from the graph we've covered in black, which is the same as 1 minus P Z less than 2.375. And then it just goes through how to locate it. So you go to 2.3 first. So it's 2.375, which is 2.3 and 0.075 added together. Okay, so if we see 0.075 and we look across the top of the table, there is no 0.075. There's a 0.07 and a 0.08. So we basically have to say, okay, well, 0.075 is exactly halfway between that. So whatever our two values are for 0.07 and 0.08, we add them together. We locate both those values, we write them down, and we divide them by 2. So you're basically finding the middle value between those two. So you find 2.3 down the left-hand side, you track across, then you track down from 0.07, you write down that value, which is 9911. Then you do the same for the one beside it, 0.08, 9913. And obviously halfway between that is 0.9912. Okay. We're still not finished yet because, again, we want to work out what the chances are being above that value. So you're subtracting that from 1 and you get 0.0088, which is obviously less than 1%. It's 0.8 of a percent, because if you multiply 0.0088 by 100 to convert in percentages, you would still be below 1%. Okay, so therefore the statement that they made originally is true. So there are just a couple of examples of how to use Z-score and the normal distribution table when working with probability.